All right, hi everyone. So let's go ahead and redo 5.54 from last night, and we'll go over A, B, and C. And we might do one other, like enantiomeric excess question, just to drive home the point. So for 5.54, the question was asking if the specific rotation of one of the compounds, carvone, was positive 61 of the S, of the S isomer was positive 61, and you had a mixture of the R and the S, and the mixture had a specific rotation of negative 55, what would be the specific rotation of the R isomer be? So I think everyone got this rule, but essentially, if I'll write it down, if the S isomer has a positive rotation, its R isomer must have a negative rotation. And and I know you know this, but just bear with me for 1 second. And if the mixture has a negative rotation, the largest component, the largest component must be R, because R was negative. And as we said last night, the R and S designation, the Kahn-Ingold-Prelog designation of stereoisomerism doesn't mean positive or negative. So negative rotation can be associated with S or it can be associated with R. And the important thing to know is those can switch. So if at a certain temperature you have an S enantiomer and it's rotating the plane of polarized light in the negative direction, so level rotatory, it's possible for you to increase the temperature at, let's say, non-standard conditions, two non-standard conditions, and make the light go to the right to become dextro-rotatory. So R and S have absolutely no bearing on um, being either level rotatory or dextro-rotatory, negative or positive. B asks the question, what is the percent enantiomeric excess of the mixture? So here we just use the equation that we see out of the book, and the enantiomeric excess percent is defined as the specific rotation of the mixture divided by the specific rotation of a pure enantiomer. You don't know which one, but unless they tell you, but just of one of the enantiomers times 100. So in this case, the question tells us that for the um, S enantiomer, it was positive 61. So we know for the R enantiomer, the rotation has got to be negative 61. So it's implied that the enantiomeric excess is going to have negative 61 in our denominator. We're looking at the R. and the mixture has a specific rotation overall of negative, oops, of negative 55. Now I wrote it in terms of R. So I wrote, negative 55 over negative 61. I could have put positive 61. And I'll show you why in a second that wouldn't have really mattered. But writing it this way maybe makes a little bit more logical sense. So if you work out the math right there, that equals 90% enantiomeric excess of or by the pure enantiomer. So the pure enantiomer, whatever it happens to be, is going to be 90% excess. And that implies that we have 10% left of the mixed component. So if we have 10% left of the mixed, the easy thing to do here, I'll show you two methods to do this. They're both easy, but this is the easier one, is to just divide whatever number we have. Here we have 10% into half being one type of enantiomer, and the other half, so in this case 5%, being the other enantiomer. Now, in this case, we knew what the designations for R and S were. So we know that the negative sign refers to R, but it didn't have to be that way. We could have not known and still have done the problem. It doesn't really matter. So here I'm going to leave it ambiguous on purpose. And we're going to say that 5% of the mixed product is going to be one enantiomer, and the other 5% is going to be um, the the opposite stereochemistry enantiomer. So if you add up one of those, that's going to be 95%. And here, that's just going to be 5%. So 5% of one enantiomer, and then 95% of one enantiomer, and 5% of another of the other enantiomer. But we know that this 95% must be the R component, because, as we already said, R was what led to the negative rotation. We just inferred that from part A, because the question kind of told us. Another way of doing it, the kind of more formal way, is to say that the total enantiomer sum in our beaker would be one type of enantiomer, percent, R or S, plus the other type, so I'll just say enantiomer prime, right? Equaling 100%, obviously. Whatever the fractions are, 50-50, 30-70, 80-20. But we also know that the enantiomeric excess percent excess equation is when you have one type of enantiomer and you subtract that from another type. So in this case, our enantiomeric excess was 90% that we calculated. So we know this has got to be 90%. That's just what enantiomeric excess means. Enantiomeric excess means the percent of R minus the percent of S that we have in our solution, or the percent of S minus the percent of R. Just which of the two enantiomers is in excess? Well, now this group of equations we can solve. We know that the plus E prime and minus E prime are going to cancel each other out. We're going to be left with two of one of the enantiomers, R and S. We don't care. We don't know which one, equaling 190%, which means that one of our enantiomers, if you divide 190 by 2, is going to be 95%, which implies that the other enantiomer must have been 5%. And we know from the information that the question gave us that the 95 refers to the R and this refers to the S. So either way, we got to the same, if you use this kind of um, old school math, that up there, you get to the same values. And I think we just answered C, which was what is the percentage of the, yeah, S carbon. So the S carbon was 5% and the R carbon was the 95%. Let me go to the other question that we had. If this recording doesn't take too long, I'll do one more problem, but let me go to the Gibbs free energy. We're not going to go through the derivation again. But what I did say last night was correct. The whole equilibrium thing. So even though we weren't talking about equilibrium, so if we have a reaction that's A plus B going to C plus D, by convention, we're referring to the forward reaction. So if we say that when delta G is less than 0, we're implying that we're going in the forward direction. We're implying that the forward direction is spontaneous, meaning the thick arrow here is spontaneous. So what does spontaneous mean? It means better likelihood Like, I think that's how you spell likelihood. Better likelihood of collision and orientation. These are my words. This is not out of the textbook. And orientation, because the way two molecules, in this case A and B, collide is important. They have to hit each other in kind of like the right way to become product. So when we say delta G is less than 0, we are saying that A and B, I should say I was going to say at a certain temperature. I'll leave that out for now. So we'll just say that A and B colliding with one another to become C and D is spontaneous. So the likelihood of that happening is very high. Can C and D go back to A and B? Sure, but that's non-spontaneous. But what if we said that for this reaction, delta G was positive? That would mean non-spontaneous in the forward direction, but spontaneous in the reverse. So going from CD back to AB. Now, in reality, both things will happen. As A and B become C and D, you're going to have more and more C and D particles forming in your beaker. They're going to start colliding, and the likelihood of them colliding and becoming A and B towards the end of the reaction is going to be higher than A and B colliding with one another because there's just not enough of them. So you'll end up reversing, but then you'll end up making more. It's like a pendulum. Then you'll end up making more A and B than you will C and D. So they start colliding. So you kind of go back and forth until you hit equilibrium. And at equilibrium, delta G becomes exactly equal to zero. So the rates of the forward and reverse reaction become the same. So I hope that kind of made sense. I was going to go over the Alene question because uh, I kind of explained it, maybe 75% of it, but not all the way. But let me see if I can do one more of the enantiomer stuff. Oh, actually, you know what? Let me finish this thought. So let's say, so we derived our Gibbs free energy equation, and we said that delta G was equal to delta H, the enthalpy, minus T delta S, the entropy. So the table that you can kind of write, the kind of conceptual table, is basically just a division between the delta H, the enthalpy change, and the entropy change. If both, and I think we did like one or two problems regarding signs. So if both are negative, and I'll just kind of repeat that here. If both are negative, so you have a negative delta S and negative H, your reaction is going to be spontaneous at all temperatures. Okay, I made a mistake. So negative for delta H and positive for delta S. You'll be spontaneous no matter what your temperature value is. If you had positive delta H and if you had negative delta S, you would be non-spontaneous at all temperatures. if you had positive delta H, and this is where it gets hairy, and positive delta S, you can be spontaneous if the temperature is high enough. And if you have basically two negatives, delta H and delta S, then you can be spontaneous even at low temperatures. And just so we have the terminology right, if delta G, the Gibbs free energy, is less than zero, we call that exergonic. And that's the same as being spontaneous. And usually, just by convention, we mean in the forward direction, right? So AB going to CD. And if delta G was positive, greater than zero, we call that endergonic or non-spontaneous in the forward direction. But it is spontaneous in the reverse. Okay, and the last thing will be the alene molecule. So remember, alene is when you have basically just three carbons all double bonded to one another. And we know that the hybridization of the central carbon is going to be an sp. So this part of the molecule right here is going to be an sp for the central carbon. But that means it's only using up one p. So it still has two p's left um, that haven't bonded with an atom. So they can make pi bonds. And that's exactly um, what that central carbon is going to do. So let's say you have one P that's like this, and we're going to label this the y-axis. Okay, so this p orbital, one of them, is going to be right there. So that's going to be the py. And then it's going to have another p orbital that is, in a sense, empty, which is going to be in the z-axis, so coming out at you. I'll try to make that a little thicker, coming out of the page or your computer screen. So this is going to be z, and then kind of like going away from you, almost like a dashed hydrogen. So that's going to be z. And we'll say that this is pz over here. And now let's say, so here is the y-axis going straight up and down. I'll draw it right there. That's the y-axis. And the other two carbons, let's say they're bonded to an ethyl group and another ethyl group on the right side. And so that's going to be an sp2 carbon right there, which means, and let's make this blue, which means this is the sp2 part of that bond. And remember, that's your sigma bond right there. The sp2. And the sigma bonds are going to be all in the x direction or in the x plane. And we'll say the carbon on the left side here, let's say the substituents that are attached to it are a methyl and a hydrogen. So we said that for the blue carbon, it was an sp2, right? So it had one more p orbital, which was, in a sense, empty to make a pi bond. And so it does. So this is the blue carbon's p orbital in the z axis, and it's going to make a bond with the z of the black. The black carbon has a y orbital that's empty, so it's going to make a pi bond with the pi orbital or the p orbital of the red carbon. So there's the y. So what does that leave us in terms of the substituents? Well, that tells us that if we take a look at the red carbon, it already has an sp2 right there in the x-axis that's bonding with the sp of the black carbon. It has a pi bond um, right there. I screwed up my letters. Sorry about that. So this should have been PZ, and here is PZ. And here's the PY, and there's the PY. So the red carbon has an x-axis and a y-axis that are occupied, which means the methyl and the hydrogen must be in the z-axis. And that we depict with a wedge and a dash. That was the point of that. And the blue carbon, all the way at the end, has a z-axis and an x-axis that is occupied, which means that the two ethyls that are substituents to it must have been in the y plane. It's the only axis left over. So these two must have been in the y. The ethyls must have been in the y. So if you get rid of all of the orbitals and we draw just the molecule the way we would normally draw it, we would see that we have two ethyls that would be just on straight lines on one carbon, and then we would have that are straight up and down in the plane, and then a methyl on a wedge, and a hydrogen on a dash. So this means that there is an internal plane of symmetry, and that symmetry is in the x-axis, like so. So up and down, there's symmetry because for the blue carbon, because it has ethyls on both sides. And because that's true on either side of the plane, so because an internal plane of symmetry exists, the molecule is achiral or not chiral.